Hi everybody, in this video I want to introduce the topic of relative velocity. Relative velocity aims to answer the following type of question. Imagine we have a turtle moving to the right relative to the ground with a speed of 0.3 miles per hour. Imagine we have a person moving to the right relative to the ground with a speed of 1 mile per hour. The question is, how fast is the person gaining on the turtle? You can rephrase that in lots of different ways. At what rate is the separation between the person and the turtle decreasing? Or once the person passes the turtle, at what rate will the separation between the person and the turtle increase? All right, and so there's an intuitive way of handling this, and it works. You might say, well, okay, a person's moving to the right at 1 mile per hour relative to the ground. If the turtle were fixed relative to the ground, the person would be gaining on the turtle at 1 mile per hour. But the turtle is still getting away from the person, so the person's not going to close the distance as rapidly. You might say, okay, well, the rate that the person is gaining on the turtle would be 1 mile per hour minus 0.3 miles per hour, and that would give me 0.7 miles per hour. And if you did that, you would be exactly right. All right, let's check another example. Let's imagine instead, still we have a turtle moving to the right at 0.3 miles per hour relative to the ground, but the person is moving to the left at 1 mile per hour relative to the ground. So they're moving to the left instead of to the right. Now, if the turtle were stationary and the person were moving to the left, the separation between the person and the turtle would increase at 1 mile per hour, at that rate. But the person's moving to the left at 1 mile per hour, and the turtle's moving to the right at 0.3 miles per hour. The separation between them will be greater than if the turtle were stationary and the person were just moving. So you might say, okay, well, to get the rate at which the separation between the person and the turtle is changing, I just add these two things. 1 mile per hour plus 0.3 mile per hour, and you get 1.3 miles per hour. And you'd be right. All right, so this seat of the pants method works for here, and this seat of the pants thing works here. All right. So in the first example, the separation between the person and the turtle is changing at the rate of 0.7 miles per hour. And in the second example, the separation between the person and the turtle is changing at the rate of 1.3 miles per hour. All right, so that's sort of seat of the pants relative velocity treatment. We want to tighten that up a little bit because when we go further with relative velocity, we have to modify the formula. It turns out that this sort of ordinary way of basically just adding or subtracting velocities breaks down when you have things that are moving at an appreciable fraction of the speed of light. All right, so we'll get to that in a future video. What I first want to do is recast this in a sort of more formal framework. So I just need a few moments to clear the board. So here's a more formal framework for looking at this. And the first thing I need to emphasize that these are x components of velocities. Later I'll take away this x subscript so that we don't have subscript overload, but it's very important to remember that these things in this formula are velocity components, so they can be positive or negative within the context of a component in a coordinate system. All right. The second thing is there's a very organized way of matching these subscripts. So here I've got P for person, T for turtle, and G for ground. And this formula will relate any three things, the velocities of any three things relative to each other. There's a very systematic way it does that. So if I want the velocity of the person relative to the turtle, I want the velocity of the person relative to the ground plus the velocity of the ground relative to the turtle, all x components. And the way you want to match these subscripts up, for the thing you want, the first subscript matches the first subscript of the first velocity. The second subscript matches the second subscript of the second velocity. And then these two are linked. So that's sort of the linking thing. So that way you'll make sure you only have three things, three velocities you've got in your problem. All right, so let's see how this plays out. Let's make sure that we get the same answer using this that we did with our seat of the pants method. All right, so first I need to actually go and put some subscripts in here. I've taken my x direction, my positive x direction to the right. So this thing that I said was 0.3 miles per hour, that is actually the velocity of the turtle relative to the ground. And that's really the x component. I'm just going to leave the x components off here. This 1 mile per hour, that's the velocity of the person relative to the ground. All right, the x component. All right, so that goes here. Velocity of person relative to the ground. Oh, and I got to make sure I've got my signs right. The turtle's moving in the positive x direction, so this is positive. The person's moving in the positive x direction relative to the ground, so that's positive. Great, so that's great. So velocity of person relative to the ground, x component is 1.0 mile per hour. Now I got to be careful here. This calls for the velocity of the ground relative to the turtle. What I have here is the velocity of the turtle relative to the ground. So let's think about this. Here's my turtle, here's my ground. If from the perspective of the ground, the turtle is moving to the right at 0.3 miles per hour, if I imagine instead holding the turtle from the perspective of the turtle, the ground is moving to the left under the turtle. So if we attach a coordinate system to the turtle, the ground is moving to the left under the turtle. The ground is moving at minus 0.3 miles per hour relative to the turtle. So plus minus 0.3 miles per hour. And this is an important point to mention something really important. If you switch the order of subscripts, you introduce a minus sign. So just to write that here, the velocity of the turtle relative to the ground, x component, is equal to positive 0.3 miles per hour. But the velocity of the ground relative to the turtle, x component, is equal to negative 0.3 miles per hour. All right, anytime you switch the order of your relative velocity object subscripts, you introduce a minus sign. Okay, so then our result is that the velocity of the person relative to the ground will be 0.7 miles per hour, as we got with our seat of the pants method. And that comes out positive. That means that from the perspective of a turtle, the person is moving to the right, closing in. All right, so let's now apply that same methodology to this second case. I'm going to rewrite the relative velocity formula, but without all the x component subscripts. All right, so again, these are x components. I'm just leaving off the x subscript so we don't have so much stuff going on. All right, so now we need to look at all our signs for everything. Now, in this case, the person relative to the ground, I wrote here a speed of 1 mile per hour, but I need to put that in terms of a velocity. If my positive x direction is to the right, well, the person is moving to the left relative to the ground, so I need to put a minus sign here, and that's going to be velocity of person relative to the ground. So in terms of a speed, it was 1 mile per hour relative to the ground, but in terms of a velocity component, I've got minus 1 mile per hour for the velocity of the person relative to the ground, x component, right? Because the positive x direction is to the right, but the person is going to the left relative to the ground. For the turtle relative to the ground, that's still positive. Velocity of turtle relative to the ground. All right, great. So now we plug in. Velocity of the person relative to the ground is minus 1.0 mile per hour. The velocity of the ground relative to the turtle, well, that'll be the negative of the velocity of the turtle relative to the ground. So I've got minus 0.3 mile per hour. All right, so I can't just plug this in. I need the velocity of the ground relative to the turtle. Why? Because I need to match these subscripts up. First one, second one, and then these have to match. All right, and so then when I add those up, I get minus 1.3 miles per hour for the velocity of the person relative to the turtle. You said, wait! When I did it by the seat of the pants, I got positive 1.3 miles per hour. Yeah, that's because I wasn't worried about signs and directions. From the perspective of the turtle, if you imagine fixing a coordinate system here, the person will be separating from the turtle at the rate of 1.3 miles per hour, but the person relative to the turtle will be getting ever further to the left of the turtle, hence the minus sign. All right, so that's how relative velocities work out in this Galileo-Newton framework. Now you might say to yourself, why would I ever want to have this messy set of subscripts? This seems like an overly complicated way to handle something that's relatively simple. Well, I have two answers to that. First of all, we've just been working in one dimension. When you're working in like 2 or 3 dimensions, you can write vector formulations of this. Once you start working in 3 dimensions, it's a little bit easier if you're really systematic about the way you do things. But secondly, and more important for our purposes, is that when we start considering speeds close to the speed of light, we need to modify this formula. And once we modify the formula, according to Einstein, to make it consistent with Einstein's postulates of relativity, our intuition will break down, and it will be very hard to use our intuition to know whether we need to just add the absolute value numbers or subtract the absolute value numbers and so forth. All right, so those are the 2 reasons. So in a future video, I'm going to show you how this relative velocity formula breaks down when we consider things that are moving appreciable fractions of the speed of light, and then we'll also do some further examples in that high-speed domain. Thanks for watching.